Okay, hello Year 10. So what we're going to do today is we're going to start to introduce the basic properties of waves, okay? So firstly, in assignments, there should be a sheet which looks a little bit like this, okay? Which is waves in action. What do I already know? You can print this off and write true or false, or you can simply write the question in your book and write true or false. That'll probably take you just a couple of minutes to get through. So what I would like you to do then is just write one sentence as to your reason why you think it's true or false, or an example. So this first one, for example, we'll go through together. Sound and light travel as waves. Do you think that's true or false? And what would be your reason, your evidence for thinking that? Now, sometimes you might not know, but you can at least have a decent stab at it because this is just what we think we know already. So pause the video and give this a go, please. Okay. So by the end of the lesson, all of you should be able to describe both transverse and longitudinal waves, what they are. Most explain the terms frequency, wavelength, and amplitude, and be able to annotate a diagram to show these terms. And a few of you link types of waves to examples. So just going back to this, sound and light travel as waves. That is true. Okay. We know that because we can actually do experiments with electromagnetic waves, such as light, and also with sound. White light is made of 8 different colours of light. That's false. We actually can distinguish 7 different colours in the spectrum. So that's red, orange, yellow, green, blue, indigo, and violet. So false, technically. Sound travels faster than light. That's false. A simple thunderclap would be a good example of that. We see the flash before we hear the thunder, or fireworks. Refraction is when light bounces off an object. That is false. That is reflection. Refraction is something different, which we're going to look at later on in this topic. Light travels at different speeds in different substances. Now, this is a bit of a strange one because light, the speed of light is given as c, which is a constant, but it's not actually true. It's constant in a vacuum. However, light does travel at very slightly different speeds through different surfaces. For example, light will travel at its maximum speed through a vacuum, through nothing, but it will slow down a little through air, slow down a bit more through water, because those materials are denser. Sound cannot travel through space. That is true, because sound requires particles, and there are no particles in space. Too much sunbathing can cause skin cancer. That is true. Ultrasound is too low in pitch for humans to hear. That is false. However, I'm not going to explain why. I'm going to come back to that in about 3 lessons' time. Ultrasound can be used for prenatal scanning, so scanning of babies. That is true. Radio waves can be used to treat cancer. Okay, that one is false, and it's a bit of a misleading one because there is something called radiotherapy, and so you might think radio waves, but actually it's false, and I'll explain why a bit later on in this topic. And your mobile phone communicates with other phones using microwaves. That is true. Okay, so mark whether they're true or false, and you can stick those in. So today, you actually already watched the video for the beginning of last lesson. So 2 types of waves which were introduced to you. The first one is what is known as a transverse wave. Now, a transverse wave oscillates up and down to the direction of wave travel, basically perpendicular. So what that means is the wave might be moving in this direction, okay? But you can see that the oscillation is in a sort of up and down motion like that. So the wave oscillates up and down while the energy travels in this direction. So firstly, can everyone draw in a transverse wave? We're going to go through a few properties for this in a moment. So leave a bit of space for this, please. And the correct definition, the oscillations are perpendicular to the direction of energy. Now, the next one you're going to draw is a longitudinal wave. Now, here you can see the energy is going the same way, that way, to the right. However, the oscillations are sort of backwards and forwards, like this, okay? Like compressing a spring backwards and forwards, okay? So the oscillations are parallel to the direction of energy travel. So the energy is traveling in that direction, and the oscillations are backwards and forwards, like that, so they're parallel to each other. Okay, so again, can you draw that in, please? And make sure you've got this definition. So to draw those in, and a quick definition would probably take you about 5 minutes. A couple of little things you need to add. A rarefaction, as you can see, is where this wave, this longitudinal wave, stretches. So here they've used the example of the spring, it stretches. And here, compression is obviously where the spring sort of bunches up. And a couple of examples of this: electromagnetic waves are all transverse, water waves, transverse. Sound waves and shock waves, such as some kind of earthquake waves, are longitudinal. Okay, so these are your two types of waves. So let's just put these up. These ones are transverse, and these are longitudinal. Okay, so can you please draw a simple diagram, but do leave a bit of space because we need to add just a few things to them, and make sure you've got the basic definitions. Okay, pause the video and do that now, please. Okay, so you can do this as a separate diagram, or you could do it as an addition to the existing one. So transverse waves are those where movement is at right angle to energy transfer. Now you need to know certain things. For example, if you just move this around, the peak is obviously of the wave, it's obviously the top. The trough, like the pig's feeding trough, is at the bottom. The wavelength, now, the wavelength, often people get confused. The wavelength is the distance from one point on the next wave, say the peak, to the same point on the next wave. So that is the wavelength. However, you don't have to measure it from peak to peak. You could measure it from trough to trough, or from middle to middle. Okay, it's the same point on the next wave. Now, a lot of people just think it's there, that's the wavelength. It's not. You've got to go to the same point on the next wave. So just for simplicity, I'm just going to leave that there. That's your wavelength. Now, the next one is the amplitude, and this one people definitely get wrong. Now, to illustrate this, you have to put a line in like that. Now, the amplitude is the distance from zero. Okay, now, as you can see, this wave goes up and down, it oscillates up and down. If it's not oscillating, the amount of energy being transferred is zero. So the amplitude is the height of the wave, but a lot of people think that is the height of the wave from peak to trough. It is not. Okay, simple mistake to make. The height is from zero to the maximum distance from zero, essentially the peak or the trough. So the amplitude is that or that. Okay, so it's the maximum displacement from zero, and that's how you would have to describe it in the exam. Okay, so the amplitude is the maximum displacement from zero, and that's how you would need to describe it in the exam. So once again, pause the video and add that to your diagram, please, with the descriptions of what specifically amplitude and wavelength actually are. Okay, so a few things to now add to the longitudinal wave. So again, they've used a wave traveling through like a spring, and I'll demonstrate this properly when we come back to school. So in this case, you can see the wavelength actually follows the same point. Okay, so here's a point on a wave. It goes to the same point on the next wave. So a longitudinal wave, although it's perhaps a little more difficult to spot, does have a wavelength. So point on a wave, same point on the next wave. Okay, so you might want to add that in to your diagram, or possibly even draw a fresh diagram just to show that clearly. Now, what happens is, because the oscillations go backwards and forwards, what happens is particles, and often these waves are through particles, bunch up. Okay, so they're squeezed and then stretched. So we call that squeezing a compression, and the stretching a rarefaction. Okay, and as I said, examples of this are sound waves. So when you hear sound, it's not like the particles physically move, and this is important actually for both waves. The particles don't physically move. So if I'm oscillating my voice, say particles in my throat, and you're hearing my voice, it's not like those particles jump into your ear. What I'm doing is I'm essentially knocking dominoes over. It's like dominoes banging into each other, going bang, 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 one after another, and transferring that energy over to your ear. So it's quite a strange thing, and I think they said it on the video. A wave is the transfer of energy with no transfer of matter. Right. So what that means is it's the energy moving through the particles that is transferred to, say, your ear in sound waves. It's not like the particles are leaping out of my throat into my voice box and into your ears. That would be gross and it would be scientifically incorrect. What's happening is I'm making those particles vibrate, and then just like dominoes knocking into each other, the energy moves through the particles in the air into your ear. Or it can be through other materials like solids or through liquids. P waves are what are known as primary waves. They're a type of earthquake or seismic waves, and those travel through rocks and we can pick those up, and those basically work like this as well. So can you now draw this in, okay, or if you have already, just add to it and make sure you've got that, please. Okay, so there are two equations that you need to know in this topic of waves. So actually, compared to forces, it's not very many. This one you will actually be given in your exam sheet. However, I'm going to show you in the next lesson how you would combine this with the other one. So basically, 1 over the frequency gives you the time period. So what you'll need to do, as always, is triangle that up. So like this, 1 over the time period. So essentially, 1 would go at the top. Yeah? Then you've got frequency and time period. Okay. Frequency is measured in hertz. 1 is just 1, and time period, as it might suggest, is measured in seconds. Now, we do need to quantify what the frequency is. The frequency is the number of waves per second. So, for example, if I have 5 waves coming past a point each second, I've got a frequency of 5 hertz. If I've got 1,000 waves a second, I've got 1,000 hertz, or 1 kilohertz. In some cases, you can get up to the millions or even thousands of millions. So a million waves passing a point each second is a million hertz, or 1 megahertz. Okay, so can you please now pause the video and copy that in? Okay, now the other equation that you need to know is this one. Speed equals frequency times wavelength. Now, a little bit confusing here. Speed, when we triangle it up, actually is the velocity of the wave. So I've had to put it in as a v. Okay, so velocity of the wave divided by frequency will give you the wavelength. So you can see I've already triangled it up for you, but I haven't put in wavelength because wavelength is denoted with a little Greek symbol called sigma. I can't draw it very well on here, but you get the idea. You'll need to look that one up in your revision guide. Okay, so frequency times wavelength equals wave speed, or velocity. There it is. And standard units for those, please, everybody. So we know that any kind of speed is measured in meters per second. We know that frequency is measured in hertz, capital H, little z, and wavelength is measured in meters. Okay, so up here, just add this. So frequency is measured in hertz, time period measured in seconds. So you can see we could actually combine these two equations. So I could say, for example, ask you to calculate the velocity of a wave with a wavelength of, say, let's just say 1.2 meters. Okay, I could ask you to work out what is the velocity of the wave. Now, a couple of little things about this. I'm just going to pause this for a second and just add a couple of things. Okay, so a typical exam question might be one like this. A wave has a wavelength of 1.2 meters and a time period of 4 seconds. What is the velocity of the wave? Okay, so let's look at what we've got. We've got a wavelength over here, and we've got 1.2 meters. However, in order to calculate the velocity, we need the frequency as well. Okay, we haven't got that. What have we got? Well, we've got a time period. Okay, 4 seconds. What's the problem though? Okay, in order to do that, it'd be 1 over the frequency. Okay, now 1 is always 1, it's always set. They're going to presume that you know that. Okay, so what we would do is 1 divided by 4, and for those of you that can do basic arithmetic, that's 0.25. We now have frequency 0.25. We then move that over here, and then it's very basic arithmetic, which hopefully you can do. Well, you probably might need a calculator for it. I know I do. 0.25 times 1.2, right, which gives us a wave speed of 0.3 meters per second. Okay, so that's an example of how you would do this. So once again, pause the video and give that a quick go. Oh, or just copy that down so you've got an example. Okay, so your final task is in assignments, and it is a sheet with some questions based on longitudinal and transverse waves of what you've learned today. And I will upload the answers at the end of the lesson for you so you can then check everything and your understanding. Okay, guys, so good luck. And as always, I'll be online if you need help.